This is Lesson 1 in our Calculus 3 series, the three-dimensional coordinate system. We're going to start by introducing the three-dimensional coordinate system. By now we're pretty comfortable with the two-dimensional coordinate system, that is the xy plane, but let's talk about what the three-dimensional coordinate system would look like. The easiest way to visualize this is to look at the corner of a room. We're going to consider that corner point the origin, and from there we're going to have our x-axis coming out towards us. We're going to have our y-axis going across. And we're going to have our z-axis going up. So here's our x-axis. And when I say our x-axis, I mean our positive x-axis. Our positive y-axis going across and our positive z-axis going up. So I think that helps to give us the idea of what our three-dimensional coordinate system looks like. Of course, we're going to draw it freehand, though, without a picture of a corner of a room. And typically, that's going to look like this. So we're going to have the positive x-axis coming forward, the positive y-axis going to the right, the positive z-axis going up. And we certainly want to make sure that our picture denotes that there are negative x values, negative y values, and negative z values. So lots of times I put that as a dotted line or whatever would be convenient for your drawing. And we'll talk about how to plot points in three-dimensional space in just a second. But you want to make sure that when you set up your axes, you have them in the right order. So I want to identify this as the right-handed coordinate system. And I want to talk about the right-hand rule. So with your right hand, if you curl your fingers from the positive x-axis to the positive y-axis, your thumb is going to give you the direction of the positive z-axis. So this is the right-hand rule in a right-handed coordinate system, and this is what we're going to be using exclusively. Now we talked about the three axes in the three-dimensional coordinate system. Let's also talk about some planes. In particular, if we take a look at the picture of the corner of the room, we can identify the floor here as the xy plane. Here, this wall, defined by the y-axis and z-axis, is going to be our yz plane. And this wall, defined by the x-axis and the z-axis, will be our xz plane. Now let's take a look at plotting some points in three-dimensional space. Let's plot, for example, 3, 2, 1. Let's see what that looks like. Remember now that this is representing x, y, and z. So it means we need to go out 3 units in the x-axis. So it's going to be helpful for me to scale these axes here. Let's see, about 3 units would be going forward about here. And then I'm going to need to go over 2 units to the y, so let me scale my y units as well. I'm just going to put in some grid lines here because I think it's going to be very helpful with our plotting, at least in the beginning, to see our grid lines. So I'm going out 3 units in the x direction, I'm going over 2 units in the y direction, and now I need to go up 1 unit in the z direction. So from here I went out 3 on the x and over 2 in the y, so now I'm here, and from here I need to go up a distance of 1 unit in the z direction. That's going to get me here. And this is our point, let's call it P. This is our point P. Just to make this a little bit clearer, I'm going to color our path in to get us to point P. So let's take a look at what we have here. We went 3 units out in the x direction, we went 2 units over in the y direction, and then we went 1 unit up in the z direction. And that gives us point P, which is 3, 2, 1. Now let's take a look at another point. Let's plot point Q, and that'll be, say, -1, 4, 3. So -1 tells us we're going to start by moving backward 1 unit. Then we're going to have to move over in the y direction 4 units, and then up 3. So again, I'm going to put in some grid lines to make it a little bit easier to see. So I'm going to start by going backward by 1 unit. So I'm going to start by going here. And now over to the right by 4 units. 1, 2, 3, 4. So now I'm here. And now I have to go up a distance of 3 units. So from this point here, I need to go up this distance. So that means I'm going to be going up 1, 2, 3 units. and this is point Q. So this is 3 units high from here. Okay. So this is point Q, and again, let's just color in that path. We're starting by going 1 unit backward, we're going 4 units to the right, and then we're going 3 units up. I think without putting in the grid lines and showing the path, it's very difficult to see where our points lie in three-dimensional space. If I were to plot points for you and I just said, okay, here's our point A. Well, where is that point? I have no idea visually what this means because I'm looking at a two-dimensional representation of three-dimensional space. So I encourage you to put in these grid lines and to show your path when you're plotting points. I think it's very important so we have an understanding of where actually those points lie in three-dimensional space. Now I'm going to be doing a lot of comparing between two-dimensional space and three-dimensional space, so I want to show some common notation. Remember that our bold-faced R denotes the real numbers. So we can talk about R2 being R cross R being the set of ordered pairs of real numbers. So this is the set of pairs x comma y such that x and y are real numbers. This is the set of all ordered pairs of real numbers. And similarly then, three-dimensional space is going to be R3. R cross R cross R. And that's the set of all ordered triples of real numbers. So it's the set of triples x, y, z such that x, y, and z are all real numbers. Set of all ordered triples of real numbers. So when I talk about two-dimensional space, I'm going to write R2. When I talk about three-dimensional space, I'm going to write R3 as we continue our lessons. Now we know in two-dimensional space the axes divide the plane into quadrants. Then in three-dimensional space the axes are going to define octants. And we talk about in particular the first octant. That's the one defined by the positive x, y, and z axes. Now for example, in R2, in two-dimensional space, what do we get when we have the equation y equals 3? Two-dimensional space is the set of all ordered pairs of real numbers, and y equals 3 is talking about all of the points that have y coordinate 3. So we know in two-dimensional space that gives us a line, y equals 3. So it's all points in R2 with y coordinate equal to 3. Now what is the same equation going to give us in three-dimensional space? So here's our three-dimensional axes. Now what does it mean when we talk about y equals 3? Well again, it's all points, but now we're in R3, all points in R3 with y coordinate equal to 3. So the y coordinates here, 1, 2, 3. So let's think about the points in three-dimensional space that have y equal 3. Let's first think about just the points in the xy plane. In the xy plane we know the z coordinate is 0, and essentially what we have is just the xy plane that we have in 2 dimensions. So we know that that would give us this line in the xy plane. Okay, but z can be anything. So actually I could take this line and we could also move it up 1 unit. We can move it up 2 units. We can move it up 3.5 units. We can move it down a couple of units as well. So essentially what we're getting here is a whole plane of points that all have y coordinate equal to 3. Similarly, in two-dimensional space, the equation y equals x gives us a line. Well, what does y equal x give us in three-dimensional space? Again, I'm going to start by just drawing the line that we get in the xy plane and then extend it from there. And again, that gets extended for any z value because z can be anything here. The y and the x coordinates need to be the same, but z can be anything. So our plane will look something like this. Let's take a look at one more graph in 2D and 3D. In R2, we have x squared plus y squared is equal to 1. And we know that that gives us a circle centered at the origin with radius 1. Okay. And now in three-dimensional space, let's take a look at the figure we get with the same restrictions. X squared plus y squared is equal to 1. Again, we're saying that z can be anything. So we're going to start out with our circle in the two-dimensional xy plane, but remember that in this equation, z can be anything, so we can extend this circle up and down, and what we're going to get is the cylinder, an open cylinder. And again, that equation is x squared plus y squared equal 1 in R3. Now, I just wanted to give you with these examples some comparisons between the same equations and how they look in 2 dimensions and 3 dimensions. But certainly in 3-dimensional space, we have lots of equations that involve z and have a restriction on z. We can take a look at just z equals 5. And now we're talking about all of the points that have z coordinate 5, right? So x could have any value, y could have any value, but z must equal 5 is what we're saying here. So let's go up 5 units. And what we're talking about is the plane z equals 5. We could identify this particular point on the plane. That particular point is 0, 0, 5, right? And we're talking about the entire plane because x and y can take any value. Just the z needs to be 5 there. Now let's go back to plotting points in 3-dimensional space and talk about the distance between points. So we know in 2-dimensional space that the distance between x1, y1 and x2, y2 can be given by the distance formula here, and that comes from the Pythagorean theorem. So let's take a look at how this extends into 3-dimensional space. So here are a couple of points in 3-dimensional space, and as you can see, I put some grid lines in with my sketch. Even though we're using these as general points, x1, y1, z1, and x2, y2, z2, I think it's helpful to have them in some sort of grid system so that we can actually see where they lie in space. So let's take a look at how we're going to find the distance between these 2 points. The first thing we want to do is kind of neglect the change in z, and we're going to take a look at this distance here. Now we can see that because we've taken away this change in z, we're really just taking a 2-dimensional distance here using the Pythagorean theorem. Now notice the x and y coordinates for point R are the same as what they are for point Q, because we didn't change the x and y coordinates, we just changed the z. So this is x2, y2. And now what's the z coordinate for point R? We changed that so that it would be the same as the z coordinate for point P. So this is z1. Okay, so now as we take our distance from P to R, we have the square root of x2 minus x1 squared plus y2 minus y1 squared. That's that 2-dimensional distance. Okay, now how are we going to get from here to the distance PQ? So this is the distance PR. What's this length here? We're going to use another Pythagorean theorem. This length here is z2 minus z1. So distance PQ is going to be the square root of, we need PR quantity squared. So I'm going to first write that like this. And then we need z2 minus z1 squared. All of that under the radical. And now what's PR quantity squared? That's x2 minus x1 squared plus y2 minus y1 squared, and then filling in here we have z2 minus z1 squared. So we can see that the distance formula extends naturally into 3 dimensions. So if, as in our picture, P is the point 2, negative 1, 0, and Q is the point negative 1, 3, 4, then the distance from P to Q is going to be negative 1 minus 2 squared plus 3 minus negative 1 squared plus 4 minus 0 squared. So that's going to be 9 plus 16 under the radical, so that's going to give us radical 41. Now let's take a look at an example. If we're given P as 3, negative 1, 2, Q as 1, 1, 2, and R as 1, negative 1, 4, is triangle PQR equilateral? How we're going to solve this, we're going to have to see if lengths PQ, QR, and PR are all equal. Now please pause the video to work on this problem. By computing the distances PQ, QR, and PR, we see that they're all equal to radical 8, or 2 radical 2, and yes, triangle PQR is equilateral. Here's another example. Let's find the distance from point 3, negative 1, 2, first the distance to the YZ plane, and then also the distance to the x-axis. So in order to get a visual with this, let's first plot the point. So here's our 3-dimensional axis system with some grid lines to help us plot. So we want to go 3 units out in the x direction, so 1, 2, 3, and then we want negative 1 in the y, so 1 unit left in the y, and then we want 2 units up. So I'm going to go 1, 2. And this distance here is copying this distance here in the z direction. So this is our point 3, negative 1, 2, and I'm just going to put in the rest of my pathway to make it easier to see where that point is. And we want to know how far this point is from the YZ plane. Where is the YZ plane? The YZ plane is when x is equal to 0. So how far away from x equals 0 is this point? It's 3 units away. That's the x-coordinate. So our point is 3 units from the YZ plane. And what about part B? How far is this point from the x-axis? Okay, here's the x-axis. Now the closest point on the x-axis to our point is going to be this one. So we want to know how far this point is from this point, 3, 0, 0. So we set up our distance formula between the 2 points. And we've got radical 5. So our point is radical 5 units away from the x-axis. Now let's talk about spheres in 3-dimensional space. But first, let's recall what we know about circles in 2-dimensional space. In R2, we know that the circle is a set of points equidistant from a given center point. That center point we normally call HK, and that distance is R, the radius. So in 3-dimensional space, we have a similar definition for the sphere. The sphere is a set of points equidistant from a given center point, and we normally call that given center point HKL. And again, that distance is R, the radius. So for a point x, y, z on the sphere, by the distance formula, we know that the square root of x minus h squared plus y minus k squared plus z minus l squared must be equal to r. So taking the square of both sides, we have x minus h squared plus y minus k squared plus z minus l squared is equal to r squared, and this is our standard equation for a sphere. So I'm just going to rewrite that over for completion. The equation of the sphere centered at HKL with radius r is x minus h squared plus y minus k squared plus z minus l squared is equal to r squared. So let's take a look at an example. Find the center and radius of x squared minus 4x plus y squared plus 8y plus z squared minus 6z equals 3. Well, let's take a look at the formula that we're given. We know that if we have the equation written in this form, it's very easy to read off the center and the radius. So what we need to do is get this equation into this form. And you've seen problems very similar to this in two-dimensional space for circles. It requires completing the square. So let's go ahead and do that. The first thing I want to do is separate my different variables. So I have x squared minus 4x, and I'm going to leave a little space, and then plus y squared plus 8y, and I'll leave some more space, and then plus z squared minus 6z, I'll leave some more space, and then equals 3. Remember that we're trying to get x squared minus 4x to be packaged in this form, x minus a number square. So what must that number be? Remember that you want to take what we have here, this negative 4, and we want to divide it by 2. So that's going to give us a negative 2, and we're looking at x minus 2 quantity squared. But x minus 2 quantity squared is equal to x squared minus 4x plus 4. So what we need to do is put in a plus 4 on this side and then a plus 4 on this side of the equal sign so that we can package this as x minus 2 quantity squared. And now similarly, how are we going to complete the square for the y terms? We have y squared plus 8y, and these need to be the first two terms in a y minus k quantity squared. So again, we're going to take our plus 8, we're going to divide that by 2, and that's going to give us 4. So we're going to look at y plus 4 quantity squared. But what is y plus 4 squared? It's y squared plus 8y plus 16. We don't have a 16, we need to put one in, and also a 16 on the other side. Then we can package this y squared plus 8y plus 16 as y plus 4 quantity squared. And now let's take a look at our z terms. We have z squared minus 6z. Again, divide this by 2. We're looking at z minus 3 quantity squared. So this is z squared minus 6z plus 9. So we're going to add in a 9 here, add in a 9 here. And now we can package this together as z minus 3 quantity squared. So what are we left with? We have x minus 2 squared plus y plus 4 squared plus z minus 3 squared is equal to, that's 20 and 12, so we have 32. So just to rewrite that, we have x minus 2 squared plus y plus 4 squared plus z minus 3 squared minus 3 squared is equal to 32. So our center, remember that to match up with our formula we need to have subtraction here. So essentially this is y minus a negative 4. And so our center is going to be 2, negative 4, 3. And our radius is going to be radical 32. And with that, we conclude Lesson 1, the three-dimensional coordinate system.